Hello everyone, so in this video I'm going to talk about nuclei, which is part of modern physics. So we're going to discuss previous year's questions which I have categorized as problem type. So after watching this video thoroughly, you have the idea how to tackle different problems in JEE Mains 2025. Let's see. Now who will get benefited from this video? So if you know basics and you have NCERT level knowledge and you have done some coaching, but still you want to improve your problem solving skills, so this video is for you because you have the idea what different types of problems are there from this chapter and you can practice accordingly. Then how to use this video effectively? First you have to revise the short notes which you have prepared for this chapter. Then write down the important information that you come across while watching the video. And whenever I discuss a problem, first you have to pause the video and then try to solve the question on your own. And if you're not able to solve, I'm here for you. Right, so first let us see the weightage. So there will be one question from this chapter which can be asked in JEE Mains. And if you look at the syllabus, so again a very small chapter. So the topics are composition and the size of the nucleus, atomic masses, mass energy relation, mass defect, binding energy per nucleon and its variation with mass number, and nuclear fission and nuclear fusion reaction. Now this is the mind map which you have the idea what different topics are there and what and subtopics are there. Now let us see the very first problem type, and it is based on the size of the nucleus. So here what you have to remember that the radius of the, here we're going to assume nucleus as a perfect sphere, and the radius will be given as some constant times a raised to power 1 by 3, where a is the mass number, right? And this r naught is equals to 1.1 Fermi. Now let us see the illustration based on the same concept. So here we have given the radius of a nucleus of mass number 64 is 4.8 Fermi. So we can say R1 is given as 4.8 Fermi and A1 is given as 64. Then the mass number of another nucleus having radius of 4 Fermi. So radius is given, R2 is given as 4 Fermi and mass number is 1000 by x. And we have to find the value of x. So here we know that R is proportional to a raised to power 1 by 3. So we can use this proportionality. So we can say R2 by R1 is equals to A2 by A1 raised to power 1 by 3. Or we can write A2 by A1 is equals to R2 by R1 cube. If you take cube on both sides. And R2, so from this we have to find the value of x. So this can be written as 1000 by x, and A1 is 64. R2 is 4 and R1 is 4.8 Fermi. So this can be written as 5 by 6. So it will be 125 by 6 cube, right? So it will be 216. So from this x comes out to be 1000 by 64 times 216 upon 125. So this will give us 8 and this will give us 8. Now from this it comes out to be 2 and then 7. So x comes out to be 27. Right, so let us see another illustration. So the mass number of a nucleus having radius equals to half of the radius of the nucleus with mass number 192. So again we can use the same formula. We have to find the mass number of the nucleus. So we can say A2 by A1 raised to power 1 by 3 should be equals to R2 by R1. And the mass number of nucleus having radius equals to half of the radius of the nucleus with mass number 192. Let us say when the radiuses are, the mass number is 192, and when the radius is say R2, the mass number is A, that we have to calculate. So A divided by 192 raised to power 1 by 3, R2 we have to calculate, R1 is R by 2. R2 is R by 2, and let me correct this. R2 is R by 2 and R1 is R, right? So this is R1 and R2 is r by 2. So this will be 1 by 2. Let us take cube on both sides. So it will be a equals to 192 times 1 by 8. Right? So this comes out to be 24. So option 1 is the right answer. Let us another question. So a nucleus having a mass number A1 and volume V1 and another nucleus having the mass number A2 and volume V2. The relation between the mass number is A2 is 4 times A1, then V2 by V1 is. So what we have to remember, the density of the nucleus will remain same. So density is constant irrespective of the mass number. So density is constant. So we can say so density for the first nucleus should be equals to the density of the second nucleus, and density will be mass upon volume, and the mass of the first nucleus will be mass of one nucleon times the mass number upon volume, that is V1, and similarly the density for the second nucleus will be mass of the nucleus, which is mass of one nucleon times the mass number divided by volume of the second nucleus. Now from this we have to find the value of V2 and by V1. So V2 by V1 is A2 by A1, and we have given A2 by A1 is 4. So it will be 4, right? So 4 is the answer. Right, so now let us see the next problem type, and it is based on mass energy equivalence relation and the binding energy and the nuclear reaction. All these three are related to each other, so that's why I clubbed all the numericals together. So let us see. Okay, right. So let me quickly tell you what is mass energy equivalence relation. So according to Einstein, that mass can be converted into energy, and the formula will be given as delta mc square is equals to the energy, right? So if delta M mass converted into energy, it will be given by this formula. And if one atomic mass unit is converted into energy, then this will be equivalent to 931.5 mega electron volt. So that you have to remember, right? Now let us see the application of this formula. The energy equivalent of 1 gram of substance. So we know the formula, right? Delta M C square is equals to the energy. So delta M here is 1 gram. So we can say 1 into 10 raised to power minus 3 kilograms, and C is the speed of light in vacuum, so that becomes 9 into 10 raised to power 16. So that is the energy, right? Now if you want to convert energy in mega electron volt, what we have to do? So 1 mega is 10 raised to power 6, and 1 electron volt is 1.6 into 10 raised to power minus 19 joules. So you have to divide joules with 10 raised to power 6 and 1.6 into 10 raised to power minus 19. So this will become 9 into 10 raised to power 13 divided by 10 raised to power 6 times 1.6 into 10 raised to power minus 19. This will give us in mega electron volt. So it comes out to be 9 by 1.6 times 10 raised to power 26, which is 5.6 into 10 raised to power 26 mega electron volt. So we can say 1 gram substance is equivalent to 5.6 into 10 raised to power 26 mega electron volt. So option 2 is the right answer. Let us see another question. It is based on the binding energy. So binding energy of a certain nucleus is 18 into 10 raised to power 8 joules. How much is the difference between the total mass of all the nucleons and the nuclear mass of the given nucleus? So when we when we add up the masses of individual nucleons, and if we compare that sum with the mass of the nucleus, it comes out it is found that the mass of the nucleus is less than the mass of the individual constituent. And why it is so? Because the decrease in the mass will add on the stability of the nucleus, right? So that energy will go into the binding energy of the nucleus. So binding energy is given as 118 into 10 raised to power 8 joules, and this binding energy will be equals to delta mc square, right? So delta m will be 118 times 10 raised to power 8 divided by 9 into 10 raised to power 16. So which comes out to be 2 into 10 raised to power minus 8. Now we have to find answer in microgram, and 1 microgram is 10 raised to power minus 9 kilogram, right? So this is in kilograms. So we can write this as 2 into 10 raised to power minus 8, and 1 kilogram will be 10 raised per, so 1 kilogram will be 10 raised per 9 microgram. So it will be 10 raised per 9 microgram. So it comes out to be 20 microgram. Option 2 is the right answer. Okay, let us see the next question. The mass defect in a particular reaction is 0.4 grams. The amount of energy liberated is n into 10 raised per 7 kilowatt hour, where n is. Okay, right. So here again we have to use mass energy equivalence relation. So 0.4 into 10 raised per minus 3. So that is the mass in kilogram. Multiply this with c square, which is 9 into 10 raised per 16. And this is equals to n times 10 raised per 7. And 1 kilowatt hour is equals to 3600 times 10 raised per 3 joules. Right? So you can say 3.6 into 10 raised per 5 or 3.6 into 10 raised per 6 joules. So now from this equation we can say n will be 0.4 times 9 divided by 36 times 10 raised per 13 minus 7 minus 5. So this comes out to be 0.1 times 10 raised to power, this will be minus 12, so this will be 1. So it comes out to be 1. So the answer is 1. Right. So let us see another question. In a nuclear fusion process, a high mass nuclide which is having a mass number 236 with binding energy 7.6 mega electron volt per nucleon dissociates into middle mass nuclide which is having a mass number of 118 having binding energy 8.6 mega electron volt per nucleon. The energy released in the process would be, so we have given say A, which splits up into B and C. A is having a mass number 236 and B is having a mass number 118 and C is also having a mass number of 118. And the binding energy per nucleon for A is given as 7.6 mega electron volt, and the binding energy for B and C is per nucleon is given as 8.6 mega electron volt. So 8.6 mega electron volt. Now, since there is so the energy is being released, so what we can say, the mass, the binding energy of the product will be more than the binding energy of the reactant. So we can say binding energy of B plus binding energy of C minus binding energy of A will be energy released. Okay, so let us put the values. So we have given binding energy per nucleon. So binding energy for B will be number of nucleon, that is the mass number times the binding energy per nucleon, which is 8.6. Similarly for C it will be 118 times 8.6, and for A it will be 236 times 7.6, and this result will be in mega electron volt. So from this we can say 236 times 8.6 minus 7.6, so which comes out to be 236 mega electron volt. So that is the amount of energy which is being released, and this released energy is denoted with Q. So Q value will be 236, right? So that is the answer of this question. Let us see the next question. If 3 helium nuclei combine to form a carbon nucleus, then the energy released in this reaction is dash times 10 raised to minus 2 mega electron volt. And we have given if one atomic mass unit atomic mass is converted into energy, then 931 mega electron volt energy is being released, and the atomic mass of the helium is 4.002603 atomic mass unit, and similarly the atomic mass of carbon will be 12 atomic mass unit, right? So we have to use this data. So we have given 3 helium nucleus, so we have atomic number is 2, mass number is 4. It gives us carbon nucleus. Atomic number is 6, mass number is 12. Right? So this is a nuclear reaction which has to be balanced, right? So it is balancing. So we have to find the energy released. So let us first find the mass defect. So mass defect will be 3 times mass of helium nucleus minus mass of carbon nucleus. So this comes out to be 3 times 4.002603 minus 12, right? So I'm using calculator, but you have to solve this on your own, right? When you get into engineering, you're bound to use calculator, right? So 3 into 4.002603 minus 12, so it comes out to be 7.809 into 10 raised per minus 3 atomic mass unit. And we have to find the energy. And we know when 1 atomic mass unit is converted into energy, it is equivalent to 931 mega electron volt, which is given in the question. So we have to multiply 931 with 7.809 into 10 raised per minus 3. So when we do that, 7.809 into 10 raised per minus 3 multiplied with 931, this will give us answer in mega electron volt. So it comes out to be 7.2701779 mega electron volt, right? So let us round off this answer up to 3 significant figures. So it comes out to be 7.27 mega electron volt, and we have to find the answer in terms of 10 raised per minus 2 mega electron volt. So that will be 727 times 10 raised per minus 2 mega electron volt. So the answer will be 727. Right. So let us see the next question. The atomic mass of carbon is 12 atomic mass unit, and for the isotope carbon 13 is 13.003354 atomic mass unit. The required energy to remove a neutron from carbon 13 if the mass of neutron is 1.008665. Okay, let us first write down the equation, nuclear equation reaction. So we have carbon 13 and we are removing neutron. So this is carbon 12 and the neutron can be written as like mass number as 1 and the atomic number as 0. Something like this, right? So this is the balanced nuclear reaction. And we have to find the energy, the required energy to remove neutron. So it is its mass number, atomic number is given, right? So that will be 13.00335 U. Okay, so what is the mass defect? So we can say it will be mass of carbon 13 minus mass of carbon 12 and mass of neutron. Okay, so this comes out to be 13.003354 minus mass of carbon is 12, mass of neutron is 1.008665. Okay, let me just quickly calculate this. 13.003354 minus 12 minus 1.008665. So this comes out to be 5.311 into 10 raised per minus 3 atomic mass unit. And we know that 1 U is equivalent to 931.5 mega electron volt. So we can multiply this delta M with 931.5 so that we can find the energy released in mega electron or energy required in mega electron volt. So 5.311 into 10 raised per minus 3 times 931.5. So it comes out to be 4.947 mega electron volt, right? And just remember one thing, the mass of, since we are supplying energy to remove neutron, so in this case the mass of the reactants, oh sorry, mass of the product will be more than the mass of the reactant. So here it should be plus, here should be minus, right? This should be plus and this should be minus. So you will get answer in positive answer. So that much amount of energy is being required. So 4.947 mega electron volts. So if we compare our answer, so option 3 is the right answer. Right, so let us see this equation, this illustration. So the explosive in a hydrogen bomb is a mixture of um, deuterium, tritium, and the lithium, right? In some condensed form. The chain reaction is given by, so we have given lithium 3 and then mass number is 6. Then there is a neutron and then we have helium and tritium. Now we have deuterium, then tritium, then helium, then neutron. So during the explosion or the energy released, we have to find the energy released in this nuclear reaction. When we have given mass of lithium nucleus, mass of deuterium nucleus, mass of helium nucleus, and we have given one atomic mass unit, when converted into energy will give us 931.5 mega electron volt. So first let us balance this. Since we don't have given mass of uh, tritium, so we can eliminate, right? So if this is the first equation and this is the second nuclear reaction, if we add these two nuclear reactions, then we can clearly see that this tritium will get cancelled out with this, right? So we're left with lithium, then we have deuterium, then and even this neutron will get cancelled out. So neutron will not come into the picture. So we are left with lithium and deuterium on the left side, and on the right hand side we have two nucleus of helium, right? And we have to find the energy released. So when the energy is being released, then the mass of the reactant will be more than the mass of the product. So here we can say the mass defect will be mass of lithium plus mass of deuterium minus 2 times mass of helium nucleus, right? So this will be 6.01690, and for deuterium it is 2.01471, and for helium it is 4.00388. Okay, let me quickly calculate this. 6.01690 plus 2.01471 minus 2 times 4.00388. So this comes out to be 0.02385 in atomic mass unit. And if we multiply this with 931.5, we'll get the energy released in mega electron volt. So 0.02385 times 931. So this will give us 22.22 mega electron volt. So option 4 is the right answer. Right. So let us see another question. In nuclear fusion reaction of an isotope of mass m, three similar daughter nuclei of same mass are formed. The speed of the daughter nuclei is in terms of the mass defect delta m will be. Okay, right. So what we have given, let us say this is the nucleus which is having a mass m. Now it splits up into three parts. Let us say each part is having a mass small m. These are the daughter nuclei, and it is going in this direction, it is going in this direction, it is going in this direction, right? Since they have same mass and the momentum, by conserving the linear momentum, we can say they will be symmetrically aligned. Their velocities will be symmetrically aligned, right? So we can say the kinetic energy of the daughter nuclei will be 3 times half m v square, right? Each of the nuclei, each daughter nuclei will be having same speed. So the speed of the daughter nuclei in terms of the mass defect. So what we can say, the energy released. So capital M minus 3 times small m. So that will be the mass defect. So m minus 3m times c square. So this is the energy released, and this energy will be acquired by the daughter nuclei in the form of kinetic energy. So that should be equals to 3 times half m v square, and we have to find uh, speed in terms of mass defect. So what is mass defect? So this is nothing but mass defect, right? So we can write this as delta m times c square times 2 by 3, and then we have small m equals to v square, and small m can be written as capital M minus delta m divided by 3. So delta m c square times 2 divided by 3m can be written as capital M minus delta m, and then we have to take the square root of this. Okay, so this capital M will be very large in comparison to small m. So in the denominator, we can write denominator as nothing but m. So we can ignore delta when we are like doing the subtraction of m and delta m. We can ignore delta m. So this can be written as root of 2 delta m c square divided by capital M, which is c times root of 2 delta m divided by capital M. So if you look at option C or option 3, that is the right answer. So whenever we have this kind of a case where we have a fission reaction going on or fusion reaction is going on, we can conserve linear momentum. The disintegration energy Q for the nuclear fission of uranium into cesium and zirconium and the neutron is, so we have to find the Q value. Right, so let me just write down the equation. So this is uranium 235, then we have two daughter nuclei 94, and then there is a neutron, right? And so in this case, the mass of the uranium will be more than the masses of the product. So we can say the mass defect will be mass of uranium minus mass of the the products, right? Sum of the masses of the product, mass of neutron. So let us put the values. So this will be 235.0439 minus this will be 139.9054 plus 93.9063 plus 1.0086. Right, let me quickly calculate this. 235.0439 minus 139.9054 minus 93.9063 minus 1.0086. So it comes out to be 0.2236 in atomic mass unit, and we have given one atomic mass unit will give us 931 mega electron volt of energy. So the Q value will be 0.2236 times 931. So that will be in mega electron volts. So it comes out to be 208.17 mega electron volt. And since it's an integer type question, so you can write this as 208 mega electron volt. So 208 is the answer of this question. Right, so let us see the next question. M0 is the mass of isotope, boron isotope, right? And MP and Mn are the masses of the photon and the neutron. Then the nuclear binding energy of the isotope will be, okay, right? So we have boron is given. So it has 5 protons and 12 minus 5, 7 neutrons, right? So we can say 5 times mass of 1 proton plus 7 times mass of 1 neutron minus mass of boron, right? So this will give us the mass defect. And if we multiply mass defect with c square, we'll get the energy, or we'll get the binding energy. So delta m times c square. So if you look at the option 2, that is the right answer. Right, so let us see the next question. A star has 100% helium composition. It starts to convert 3 helium into 1 carbon via triple alpha process. So triple alpha means we are using 3 helium and we are getting 1 carbon. So this will give us 1 carbon and some energy is being released. The mass of the star is 2 into 10 raised to power 32 kilograms and it generates energy at a rate of 5.808 times 10 raised to power 30 watt. The rate of converting these helium to carbon is n times 10 raised to power 42 per second, where n is. So we have to find the n value, right? So what we can do in this case, we have given power, right? So from the power we can find the amount of energy which is being released in 1 second. So we can say in 1 second the energy released will be 5.808 times 10 raised to power 30 joules, right? And we can see when 3 helium are getting converted into carbon, then Q value of the energy is being released, right? And it is also given the rate of converting. So let us first find the energy released in one reaction, right? So let us first find the mass defect. So mass defect will be 3 times mass of helium minus mass of carbon. So that will be 3 times 4.0026 minus 12, right? So this will be 3 times 4.0026 minus 12. So it comes out to be 7.8 into 10 raised to power minus 3. Now let us multiply this with 931.5. So 7.8 times 10 raised to power minus 3 times 931.5. So this will give us 7.26 mega electron volt of energy. So we're getting 7.26 into 7.26 mega electron volt of energy in one reaction, and we can convert this energy in SI units. So 7.26 times 10 raised to power 6 times 1.6 into 10 raised to power minus 19 joules. So that much amount of energy is getting produced in this reaction, in one reaction. So that will be 11.625 times 10 raised to power minus 13 joules, right? Now from this we can find the number of reactions happening in 1 second. How we can do that? So we know in 1 second 5.808 into 10 raised to power 30 joules of energy is being released. So number of reactions per second will be 5.808 times 10 raised to power 30 divided by 11.625 into 10 raised to power minus 13, right? So if we simplify this, 5.808 divided by 11.625, so this gives us nearly 0.5 into 10 raised to power 43, or we can say this will be 5 into 10 raised to power 42 reactions per second. And we have to find the rate of conversion of helium. So we know that in one reaction 3 heliums are being used, right? So to convert, so we know now we know the number of reactions happening. So the rate of converting of helium to carbon will be 3 times 5 into 10 raised to power 42, because there are 3 helium involved in one reaction. So it will be 15 into 10 raised to power 42 per second. So that is the rate of conversion of helium to carbon. So N comes out to be 15, right? So 15 is the answer of this question. Right, so let us see the next question. The energy released in the fusion of 2 kg of hydrogen deep in the sun is EH, and the energy released in the fission of 2 kg of uranium is EU. The ratio of EH over EU is approximately. So we have to find the ratio of the energy released when we are using 2 kg of hydrogen and 2 kg of uranium. And the reaction is also given. In fusion, we have given 4 times 4 protons plus 2 electrons, so it will be 0 and this will be -1. It gives us helium, right? 2 4, and neutrino plus some photons and 26.7 mega electron volt of energy. So in one fusion reaction, the energy released is 26.7 mega electron volt, and then in the fission reaction we have given 200 mega electron volt, and the Avogadro number is given as 6.023 into 10 raised to power 23, right? So what we can say, to produce 26.7 mega electron volt, how many protons are being used? 4 protons, right? So we can say 4 grams will produce how much amount of energy? That will be 26.7 times Avogadro number, right? And that will be in mega electron volt. And so for 2000 grams, it will be 26.7 times Avogadro number divided by 4 multiplied with 2000. So that will be, which is in mega electron volt, and this will be EH. Similarly, we can find EU. So we know that 235 grams produces 200 mega electron volt of energy into times n naught also, right? And for 2000 grams, it will be 200 times n naught times 2000 divided by 235 mega electron volt of energy. So that will be EU. Now we have to take the ratios of these two energies. So we can say 26.7 times n naught times 2000 divided by 4, and this divided by 200 n naught times 2000 divided by 235. So that will be EH upon EU. So this 2000 will get cancelled out, n naught will get cancelled out, and let us simplify this. So 26.7 times 235 divided by 800. So it comes out to be 7.84. So this ratio comes out to be 7.84. Now let us check the closest answer. So we can say option 1 is the right answer. Right, so the last problem type that we have to discuss is liquid drop model of nucleus. You should know just the basics of this, and then you'll be able to crack the problem. So let us see. Anyway, you'll study about this in depth in your college. So let us see what this model is all about. According to Neil Bohr and Kalkar, so they propose that if we treat like the nucleus just like a liquid drop, then we can draw some similarity and we'll be able to study the binding energy of the nucleus. And later, Weizsäcker and the Bethe, they proposed a semi-empirical formula, and based on this formula, they were able to explain the nature of the binding energy per nucleon versus mass number curve. You must be familiar with this curve, right? It tells us the stability. Greater the binding energy per nucleon, more the stability. So in that semi-empirical formula, they have considered 5 energies. So first is the volume energy, second is the surface energy, third is Coulomb energy, and the fourth is asymmetry energy, and fifth is pairing energy. So what you have to remember, that volume energy will try to increase the binding energy and it will be proportional to the volume. And we know that radius of the nucleus is proportional to a raised to power 1 by 3, where a is the mass number. So the volume will be proportional to a. So that's why the volume energy will be proportional to A. So the binding energy has 5 terms, and each term corresponds to these energies, right? So we have volume, surface, Coulomb, asymmetry, and pairing energy. Similarly, surface energy is proportional to the surface area, and so that will be r square, proportional to r square. So it is proportional to a raised to power 2 by 3. So surface energy will try to decrease the binding energy. There is a negative sign here. And if you talk about Coulomb energy, it is the interaction between the protons inside the nucleus, and it will try to reduce the binding energy. And how many protons we have? Z numbers of protons. So how many pairs will be having? Z times Z minus 1 by 2. So that's why there is a factor of Z times Z minus 1. And since the potential energy between two protons depends upon the distance between them, inversely proportional to the distance between them, so we can say the Coulomb energy will be inversely proportional to the radius of the nucleus, and so that's why it is divided by a raised to power 1 by 3. Similarly, asymmetry is depends upon the difference in the number of neutrons and the number of protons in the nucleus. So this 8 minus 2z is nothing but the number of proton minus number of neutron square, and it will be inversely proportional to the mass number. Again, it will try to decrease the binding energy, right? So if we have asymmetry, it will try to decrease the stability. And the pairing energy is like if we have even number of neutron and even number of protons, so that will increase the stability of the nucleus. So that's why it will try to increase. So we'll have a plus sign here. And if we have even number of neutron or odd number of proton, or odd number of neutron or even number of proton, it does not hamper the stability. So there will be no change in the binding energy. But if we have odd number of neutron and odd number of proton, it will decrease the binding energy. And this pairing energy is inversely proportional to a raised to power 3 by 2. Only that much you have to remember. Okay. So let us see the question based on this concept. For a nucleus X having mass number A and atomic number Z, so we have given 5 statements and we have to figure out which of the options is correct. So statement A is the surface energy per nucleon is A1 times A raised to power 2 by 3. First, so they are saying positive, right? So it has to be negative, so it is incorrect. The Coulomb contribution to the binding energy is minus A2 times Z minus 1 upon A raised to power 4 by 3, but it is A raised to power 2 by 3 in the denominator, so this is incorrect. Volume energy is A3 times A, so that is correct. Decrease in the binding energy is proportional to the surface energy. This statement is ambiguous. Let us see the statement E. While estimating the surface energy, it is assumed that each nucleon interacts with 12 nucleons. So it is not possible for the surface molecule to interact with 12 nucleons, so this statement is incorrect. Now if you look at the option, let us use elimination technique. So option A is incorrect. So A is coming in statement 3. Option B is also incorrect. So 2 and 4 are incorrect. So we can say the most appropriate answer would be option 1. Now let us see the next question. For the statement given below, so again we have given 5 statements and we have to choose the most appropriate answer. The angular momentum of an electron in nth orbit is an integral multiple of h, so that is fine. Option A, statement A is correct. Nuclear force does not obey inverse square law, that is also correct. Nuclear force are spin dependent, right? So it depends upon the orientation of the interacting particles, so that is fine, that is correct. C is fine. So nuclear force are central and charge independent. So central forces only depends upon the distance between the two interacting particles, but nuclear force also depends upon the orientation, what is the spin of the two charged particles. So statement D is incorrect. Let us see the statement E. So the stability of the nucleus is inversely proportional to the value of packing fraction. Now what is packing fraction? So if you were to consider any nucleus, its mass number is a whole number, right? But the actual mass is not a whole number, right? So there is some deviation between the two masses. So packing fraction is defined as the actual mass minus mass number per unit mass number. So that is defined as the packing fraction. So as we increase the packing, as the packing fraction increases, stability decreases. So option E is correct. So if you look at the option 3 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.